just wanted to go through some of these Punnett square problems that a couple of people have contacted me about. So we'll start with a simple one, non-sex linked. So silkworms, the dominant allele for cocoon colour is yellow. So yellow is dominant. So maybe we would choose a capital Y to indicate the dominant allele, and then the recessive allele is the white cocoon. So we're going to have to use lowercase y because we always use uppercase for dominant and lowercase for recessive. And of course, if this is recessive, you would need two small y's for a white to occur, and for a yellow cocoon to occur, you could have, if there's one or two big Y's, you're going to get that yellow cocoon. With parents with two genotypes, they've given you the genotypes, YY and YY. What will be the possible genotypes, the genes, and the phenotypes that their offspring could produce? Okay, so assigning alleles, they've already given us the letters. Assigning alleles is when you choose a letter that you're going to use, and we use big Y for yellow and little y for white. Could have used any letter, but that's what we've got at this stage. So the parent genotypes, they gave those here, big Y, and little y, little y. Now, the gametes are the potential sex cells that could be passed on, and of course they'll only have half the number of chromosomes and half the number of genes. Now this parent can only pass on a big Y. That's why it only appears once here. You could put or another Y, or big Y. And the same over here, you could put just Y by itself for little y, or little y, or little y. It's one or the other. But this parent can only pass on big Y's, and this can only pass on little y's. So that's why this Punnett square looks a bit odd, because if you can only pass one on in each case, all the offspring will be like this. Nothing to stop you from doing the full Punnett square. Don't lose any marks. Big Y, little y, and you fill that in, and you come to the same conclusion, that 100% of the offspring will be heterozygotes, meaning one of each allele. So the genotype ratio, the genotypic ratio of genes, is 100% big Y, little y, and the colour that we would see of the cocoons, of course, 100% yellow, because only if there's even one big Y present, because it's dominant, it's going to be yellow. Now, the second one we have here is Tay-Sachs. Autosomal. Autosomal means it's just a body cell, okay, not sex-linked. And it's a recessive condition. So straight away, maybe we put a T there. You can start to fill things in before you even get to the questions. Recessive condition for Tay-Sachs, fatal damage to the nervous system, complete Punnett square. The couple are both unaffected, but they're carriers. Of course, a carrier is a person who carries a recessive gene, but themselves, because they have a dominant gene, they're not affected. So if they're carriers, they're going to be big T, little t, and big T, little t. That's just the way it must be. And here we can see assigning alleles. Well, we've already chosen T for little t is Tay-Sachs, and big T is unaffected, and I've written that down there. Not just big T, little t, I have to use the words to say what they indicate. The genotypes, the genes that the parents have, big T, little t, and big T, little t. What can they pass on to offspring? Well, it could be big T or little t from parent 1, and the same for parent 2, big T or little t, one or the other. And now we're starting to get our Punnett square. There's our Punnett square, big T, little t, big T, little t, and there's our rate. Now we've seen this one before. So we've got 25% is big T, little t, 50% is big T, little t, and 25% is little t, and that's what we've written here, but we used 1 to 2 to 1. That's actually a ratio from mathematics. Nothing to stop you from putting 25% big T, 50% big T, little t, and another 25% little t, little t. You can even use halves and quarters if you wanted to. And nothing to stop you, as long as we're clear that you understand what proportions we have. Phenotypic ratio, the phenotype is what we see. So this one here, this one here, this one here, because there's a big T present, will be unaffected. They will not show symptoms of Tay-Sachs. Any children unfortunate enough to have the double recessive will be little t, and they will have Tay-Sachs, 25%. What's the percentage likelihood a child will have this condition? 25%. Now, the next one is, oh, that's an odd looking Punnett square, but similar logic to what we saw before. Huntington's disease, autosomal, meaning just normal cells again. It's a dominant condition. Nasty. So we'll give it a big H. I'm just choosing that right now for Huntington's disease. Yes, some extra information about brain cells decaying. That's terrible. Complete a Punnett square where the wife carries a single allele. If she's got that big H, she has the condition. And it's indicating because it's single, she must be a heterozygote. And her husband is unaffected. Now, if he's unaffected and it's a dominant condition, he must have little h. Has to have. So now we've got our alleles, big H for Huntington's, little h for unaffected. The parent genotypes, big H, little h, and little h, as we said. What can each parent pass on as sex cells, as gametes? The mother could be big H or little h, one or the other. The father can only pass on little h. Now you could just do one, or you could say little h or little h, same thing. And then you draw your Punnett square. Now if you want to do the full Punnett square, feel free. And you can put the father in there and it comes out exactly the same way. Exactly the same way. Here is the mother, here is the father, big H, little h, and the same down here. So you can see it's a 50-50 split. So you've got, for every big H, there's a little h, or you could put 50%, 50%, or you could put half and half. 50% of children will be a carrier, there's no getting around that, and 50% will be unaffected. And I used the word carrier, that was incorrect. Of course, 50% of children will be affected. They will have the condition because it's a dominant condition. And 50% will be unaffected. Percentage likelihood a child will be born with the condition, 50%. No such thing as a carrier for a dominant condition. Menkes hair disease, boom, sex-linked, recessive. So if it's recessive, if it's sex-linked, it's X, and it's recessive, it's a little letter. And so we're going to choose X, little m, to indicate a recessive condition on the X chromosome. Let's see, Wendy is a heterozygote. She's got to be an XX, and a heterozygote means one of each. So she's got a big M and a little m. So she is in fact a carrier. She's not got the condition, but she carries the gene. And Peter has Menkes. So on his 1X, he has a little m, and then he has a Y. And so here's our parent genotypes. We've already worked these out here as we went through the sentences. Okay, highlighting our key words. Parent genotypes, Wendy and Peter. Remember, the Y doesn't have it. Don't put it there. Parent gametes. Wendy can pass on an X with a little m or an X with a big M. One or the other. Peter can pass on an X with a little m or a Y. Okay? So he could contribute an X to produce a daughter or a Y to produce a son. And when we draw our Punnett square, there's Wendy, X, X, big M, little m, and there's Peter, X with a little m and a Y. And here are the sons. X, big M, Y, so recessive, so this child is unaffected. X, little m, Y, we have a son with the condition. X big M, X little m, a daughter who is unaffected but a carrier, and X little m, and a daughter who is unaffected in every way. Now the genotype, annoyingly, you'd have to write out each one. It's 25% this, 25% this, 25% this, and a final 25% this. And or you've got a ratio of 1 to 1 to 1 to 1, okay? Meaning 25%, 25%, 25%, 25%. So it's a bit of a mixed bag. That's the genotype. Phenotypic ratio, we have for, it's saying 50-50. So we have an affected child here, and, did I get that one wrong? That is, of course, an affected daughter here because it's a recessive condition. I hope I didn't get that wrong earlier. So I've got 2 of potential children affected, one a son, one a daughter, and 2 potential children unaffected. So 50% will be okay and 50% affected. And that's where we get a 50% from. Okay? And next one, we have, the good old pedigree tree. So let's have a read. Scott is a male. I know this is an X-linked condition because I read it earlier. So if it's X-linked, it's of course sex-linked. It's the X chromosome. So Scott is XY, and his sister is XX, because she's a girl. And it's an X-linked dominant disease. Okay, that's unfortunate. So we're going to put big M for Scott and a big M here for Taffy. That's all we can know at the moment. Their father is unaffected. Now if the father, it's mentioned the father specifically, so he must be XY and he must be a little m, because of course it's a dominant condition. And if he's a little m, that's the X he would give to his daughter. Okay? But she's got one big M here, and the father must have contributed the little m, because he's an unaffected, and any daughter is going to get that X from him, so that must go over there, and we know she has the condition, so that must come from the mother. So we've got all this information without even having looked at the pedigree tree, and you can even work it out from the pedigree tree, the same thing. Let's ignore all that. There's big block-headed father, he must be XY with a little m because he's unaffected. The mother here must have at least one big M, and we wouldn't know that. We have an affected son. The Y is going to him. If he's got the condition, he must have got that from the mother, the big M from the mother, and we have an affected daughter. Now, the father here has given the little m, so the big M must have come from the mother. We still don't know this one here, so there's a little m. The big M comes from the mother. Geez, I've really got to get these M's right. Maybe don't use M in the future. It's a bit better when you type it, okay? And so we know the mother is definitely got the condition, okay? So the condition is dominant. The father must be X, little m and Y, because he isn't affected. The daughter is affected, so must be little m and big M on her X chromosomes, because the father can only pass on the little to her. The son can only be big M and Y, so he's gotten that from the mother, and the mother must be little m, big M. And I'm going to have a think about that myself for a moment. I've missed something as I've gone through, because I didn't fill in that before. Right, the daughter is getting, of course, if the daughter's getting the little m from the father, then she must have gotten a big M from the mother, okay? Son is Scott and his younger sister Taffy. Yes, okay. So the mother must have a big M, little m heterozygote condition, okay, in order for that pedigree tree to work. Now, lastly, this is alleles. Oh, there are the alleles for this situation. You have the father here unaffected, and the mother here is a heterozygote, and then subsequently the Punnett square. A daughter with two little m's, a son with a little m coming from the mother, okay? The daughter, little m, big M, and a son, affected son, coming from the Y coming from the father, the X from the mother, okay? So there are the parent genotypes that we just spoke about before, and of course the gametes that could be passed on would be X or Y, and with their respective alleles, little m from the father, little m and big M from the mother. There's our genotypic ratio. Again, it's 25% of each, which is pretty common with these types of conditions. And so the chance that a child will be affected is 50% chance affected, 50% chance unaffected. Okay. Lastly, this one causes students a lot of trouble, but it's actually reasonably straightforward. Okay, right. So what we have here is Tom is a male and has Gault syndrome, which is X-linked dominant. So because I was lazy, I chose the same letters. So if it's dominant, it's a big M. Okay. Now Tom has the condition. His father also had the condition. So the Tom, his genotype must be X. He suffers from the condition. It's X-linked, so he must be a big M and a Y. The father also suffered from the condition, X, big M, Y. Now, Tom's brother doesn't have the condition, X, little m, Y. Now remember, the father is giving the Y in each case to his sons, which means the X, this X here came from the mother, and this X here came from the mother, which means the mother must be a heterozygote with a big M and a little m. Okay? Because fathers always pass Y to sons. And so there we go. Assigning alleles, X, big M for Gault's, X, little m for unaffected. Parents' genotypes, X, big M, Y for the father who's affected, X, little m, big M for the mother. So she has the condition, she's got that single big M. Parent gametes, you can pass on one or the other, and you fill in your Punnett square. So here's a X, big M, Y, there's an affected son, Tom, X, little m, Y, this is his brother, that is unaffected, X, big M, X, little m, so a daughter could happen that has the condition, and she has a double copy of the dominant condition. X, big M, X, little m could also happen, in which case this daughter would be affected. So you can see here, this is dramatically bad. 1, 2, 3 affected children. There is a 75% chance that a child born would be affected under this situation. Tom's mother must suffer from the condition because Tom inherited his affected X chromosome from her, and his brother affected Tom's brother inherited the not affected chromosome, X chromosome from her. So Tom as a boy, he could only have inherited the Y chromosome from his father, and he must have inherited the affected X chromosome from her. Well, I hope that helps you out and makes those Punnett squares a little bit clearer.